Okay, so the second thing that we want to talk about today is called the cardinality. Or the size of a set. Okay? Okay, so you have a set A. Last time we have talked about we can use this one to denote the number of items in A. Okay? Okay? So there are two cases. Okay? There are two cases. If this one is finite, so if this one is some number that you can tell, so maybe it is a set that contains 0 items, or it is a set that contains 1 million items, then we call it, so this is a finite number, okay? Then we call it a finite set. So if the size of a set is finite, then it is a finite set. Is that okay? On the other hand, if a set is infinite, then we call it an infinite set. Okay? So sets, you can roughly talk about the division. So it is a finite set and it is an infinite set. Okay? But we have another classification. Okay? Okay, so let me give you some examples. Okay? So for instance, what are the possible examples of an infinite set? Okay, infinite set example. For example, the set of natural numbers. So the set that contains all the numbers from, natural numbers is tricky, okay? Sometimes people count it from 0, 1, 2, 3 up to infinity. And sometimes people count it from 1, 2, 3 up to infinity. But in any case, the set of natural numbers in whatever definition, it is infinite. Is that okay? And then there is another. So for instance, the set of real numbers. It is also an infinite set, right? We can also have the set of rational numbers. So what is a rational number? I hope you still recall. Square root 2 is not rational. 0.5 is rational. So a number is rational if it can be expressed as a ratio of 2 integers. So the set of rational numbers is infinite. The reason is that rational numbers will properly include all the natural numbers, right? So if you have a natural number 3, then you can think of this as 3 over 1. If you have number 5, you can think of this as 5 over 1, okay? So the rational numbers will contain all the natural numbers. So if there are infinite items here in the natural numbers, then there will be infinite numbers in the rational numbers. Is that okay? Okay? Good. And so these are examples of infinite set. And okay, now, so usually the set of natural numbers, we will denote this by n. Is that okay? The set of real numbers, we will denote this by r. Okay? And how about this one? The set of rational numbers, we will usually denote this by what? Q. Okay. Yeah, why Q? I don't know. Perhaps it is Q, I don't know. Quotient of 2 integers, maybe, I don't know, but usually it is Q, okay? Good. Now, this is something interesting. Okay, so for mathematicians, they will they are not satisfied just by counting the size of an finite set. They also want to have some idea of what is the size of an infinite set. So they define. So this is just define. So they define, okay. The size of a natural number set. So the size of this one. So they give it a label. So they define it to be, this is infinite, of course, but it is, okay, maybe what kind of infinite? So they define it to be equal to a symbol like this, okay. So this reads as Aleph. This symbol reads as Aleph. So it is Aleph naught or Aleph 0. Okay. So they call the size of natural numbers Aleph 0. Okay. So what is Aleph? Aleph is a Hebrew letter. So it is the first letter in the Hebrew 希伯来文. So Hebrew, so it's the first letter in the Hebrew alphabet. It's like A is the first letter in the English alphabet, or what? Or yeah. So for different kinds of alphabet, you have the first letter. So Hebrew, the first letter is Aleph, and they borrow this Aleph symbol for this. So it looks like what? It looks like a soldier with a shield in front of protecting him. It looks like this letter. So this is Aleph 0, okay. And then they also define what? They define, okay, if a set, okay, if for some set, let's call it A, such that we can establish a one-to-one correspondence between the items in A and the numbers in N, then we will also say the size of A is the same as the size of N, which is equal to this Aleph 0. Is that okay? Okay. So here there is a word that we have not defined. So this is something that is going to talk about in the next topic, function. But here, one-to-one correspondence means that I pick an object in A, I can get a unique object in B, in this N, such that these two forms a pair. So any object here, I can pick another object there to correspond to that. So if I can establish a one-to-one correspondence between this set A and this set N, so this correspondence is, on the other hand, if I pick an object in N, I can also find the correspondence. What is the object in A that corresponds to it? So if there's one thing here, I get one thing here, one thing here, I get one thing here, then the two sets should have, okay, equal size. Does that make sense? Yeah. So naturally, if you want to compare two sets, two finite sets, how do you compare? One way is you count the number of items in one set and count the number of items in another set and find out which one is larger, which one is smaller. But on the other hand, there is another way. Another way is that you pick an object in the first set and then you find an object in the second set. You cancel these two. You pick another object in the first set, you pick another object in the second set, right? And both cancels. So if you can find out a correspondence, one-to-one correspondence between the two sets, then you know that these two sets will be the same in size. On the other hand, if one runs out first and the other still has some items, then you know that this side is larger. Is that okay? Okay. Now, this is for infinite set. Infinite sets, you cannot count the size before you compare, because this is infinite and this is infinite. You are going to run out of your life to find out which one is larger. So mathematicians tries to come up with how to compare two infinite sets. Is to pick an item here, you find an item there. Or you find an item here, then you pick an item here. So if you can always find the correspondence between this side and that side, then they will have the same size. Is that okay? Okay, now this is the difficult part. This is the most difficult part. It is because based on this definition, you will now have some confusion. Okay. So first of all, this is the first confusion that I want to give it to you. So assume that natural number starts from 1. So 1, 2, 3 up to infinity. So for our convenience. So I'm asking, okay, so consider the set of all positive even numbers. Positive even numbers. So you have 2, 4, 6, 8. Okay, so this is a set. Is that okay? And now you have the natural number. 1, 2, 3, 4, 5, 6, 7. Which set is larger? Or do they have the same size? What do you think? Okay, what do you think? Which set is larger? So one of them is, okay, so one of them is all the even numbers, forget it, and the other is the natural numbers. Okay, so natural numbers. So you start from 1, 2, 3, ... Okay, and then for even numbers, let me give it a name. So let's call it E. So the even numbers, you have 2, 4, 6, 8, and so on. Okay, this is what I want to ask. What is the cardinality of E? Will it be smaller than this Aleph 0 equal to this Aleph 0 or larger than this Aleph 0? Yeah, 0. And first of all, could it be larger, right? It couldn't be larger. Yeah, the reason is what? You notice that this E is a subset of this N, right? So normally, we can reject this case. It couldn't be larger. It couldn't have more things than the natural number. But should it have fewer things, or should it have equal number of things? So if you think this is less than, could you please raise your hand? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Okay, 10, 11. Okay. If you think this is equal, could you please raise your hand? Good. Okay. So there are two. Yeah, this is what I want. Yeah, there are two different groups. Okay. One says equal, one says less than. Okay. The reason it is less than, it is because it is a subset, right? Now, how about equal? So for equal, so for those who can come up with equal, that means that they believe that there is a one-to-one correspondence between the two sets. Let's find out. Is there a one-to-one correspondence? Yeah, the one-to-one correspondence is easy to establish, because if you pick 1 here, I can pick a 2 here. If you pick a 2 here, I can pick a 4 here. Okay? If you pick a 3 here, I can pick a 6 here. Is that okay? If you pick any number x in the natural number, I can find out the number 2 times x that appears in E, which is not matched with any other person. Okay. On the other hand, if you find out any number in this side, for instance, I have an 8, then I can find out what is correspondence in N. I just divide it by 2, and then I find the correspondence. That means that at any time, Whenever you have an object in N, I will have a corresponding object in E, and it never runs out. So in this sense, okay, we are saying that these two sets are having the same size. Okay, so this is the case. So it turns out that this is this one. Okay? Is that okay? Okay? Strange, right? Okay? But correct. Okay? Now let's look at another example. Okay, how about this one? This time I have, now this is difficult. Okay, another difficult thing. Set. Set is usually used to represent integers, positive or negative. So it contains -2, -1, 0, 1, 2. Okay. Now, so you will see that the natural number n is a subset of this set, right? So we notice that this is a subset of this set. Okay, so usually there's a subset of this set. So I want to ask, what is the cardinality of this set? What is the size of this set? Is it going to be greater than, so, or equal? Okay, either greater or equal than this LF0 or LF. Which one? Okay. Which one? Which one? What do you think? You think it is equal? Could you please raise your hand? Okay, 1, 2, 3, 4. Okay. If you think this is strictly greater, could you please raise your hand? Okay. Okay, good. Okay. So there are still divided opinions. That's great. So if you think this is greater, it is because you believe that, okay, so first of all, this is a superset. This is much larger than this one. And you believe that there is no one-to-one correspondence. On the other hand, if you think this is equal, that means that you think that there is still a one-to-one correspondence between the sets of N and Z. Okay, now it is equal. So to show that it is equal, I just need to give you one particular correspondence. And this is the correspondence I'm going to give you. So I'm going to correspond 0 to the 1 in the natural numbers. Is that okay? And then 1 corresponds to 2. -1 corresponds to 3. 2, I corresponded to 4. -2, you corresponded to 5. Is that okay? One time to the right side, one time to the left side. One time to the right side, one time to the left side. Is that okay? Now, this is a one-to-one correspondence. The reason, okay, the reason is that, so if I pick any number here, for instance 7, okay, then using this scheme, there will be a particular natural number mapped to this 7. Is that okay? Does that make sense? Okay, so if I have a number here, I will find a corresponding number there. Is that okay? And similarly, if I have a number here, let's say the number 5, then using this process, I will always find a particular number in this group set such that it corresponds to the 5 there. Is that okay? Although the corresponding function may not be easy to compute, but I know that there is a way that every number here corresponds to a particular number here, and every number here corresponds to a particular number there. So this establishes a unique one-to-one matching or correspondence between the two groups. Okay, so in that sense, they are having the equal size. Is that okay? Is that okay? Okay. One more. Okay, so okay, so let's define a group called P, the prime numbers. So the prime numbers are 2, 3, 5, 7, 11, 13, 17, blah, blah, blah. So these are prime numbers. Now we have shown what? We have shown earlier that the set of prime numbers is infinite. Okay, so the size of P is infinite. So we know that this is infinite. is infinite. And also what? We also know that this okay, so we also know that the set of prime is a subset of this natural number, right? Now, my question is, how about the cardinality? Is it going to be, so there are two cases, is it going to be less than this LF0, or is it going to be equal to this LF0? Okay. If you think this is equal, could you please raise your hand? Good. If you think this is less than, could you please raise your hand? Okay. Good. It is equal. How do you show that it is equal? You find a way to find the correspondence. So I am going to give it to correspond to 1 in the natural number, 2, 3, 4, 5, 6, and so on and so forth. Okay? So the corresponding function is difficult to write down. But you can see that, okay, every integer in n, you find a correspondence here. The number 7 in n corresponds to the 7th smallest prime on the right-hand side. Is that okay? The number k, so if you have a number k here, corresponds to the k smallest prime here. Okay, so that means that every integer in n, you can find a correspondence here. And how about this side? How about this side? I have a prime. So let's say 101 is a prime. So what do I have a number that corresponds to it? Easy. Yes, there must be. Because 101, you know that it must be a certain smallest prime. Maybe it is the 21st smallest prime or the 23rd smallest prime. I don't know. But it is, let's say this is the rth smallest prime. Then it will correspond to the integer r in the natural set. Is that okay? So that means that whatever you have a number here, then you can find a correspondence to this side. Is that okay? Okay, which correspondence is difficult to find? Yeah, I think the correspondence is easy. Okay. It is easy because for this set, you can find a rule that lists out all the elements here. So for instance, the rule here is you first list out the smallest prime, and then you list out the second smallest prime, and then you list out the third smallest prime, and so on and so forth. By doing this listing process, listing the first smallest prime, the second smallest prime, the third smallest prime, you're actually giving the correspondence. Because the first smallest prime corresponds to 1, the second smallest prime corresponds to 2, the third smallest prime corresponds to 3. Is that okay? And for this one, you give a rule. You first list out 0, and then go right, list out 1, go left, list out -1, go right, go left. You have a rule. Okay? This rule allows you to list out everything one by one. Okay? So this is the general theorem. If a set of size infinite, such that there is a rule to list out the items one by one, every item can be listed. You are sure that every item can be listed. Then in that case, that set is what? Has the same cardinality as the natural number. And we give it a name. For any set that has a one-to-one correspondence, okay. For any set, so let us do the break a little bit later, okay? Yes. So we call this set A is called a countable set. Well, countable sets. Let me see. I should be more careful. Okay. So we give it so we have another classification. Sets can be countable or uncountable. Okay, if a set is countable, either it is finite or the size of that set is equal to this LF0. Otherwise, the set is called uncountable. So for all the infinite sets that is countable, then there is always a listing rule. If you can list the item one by one, 1, 2, 3, 4, 5, you can list them out, then this is a countable set. Otherwise, it is an uncountable set. Okay, so we are going to have a break, but think about this over the break. So I hope you to find out this. Okay, so we've talked about sets. I have this question. Okay, so for rational number, let's do this for positive rational numbers. I want you to show that this is also a countable set. So the size is also of LF0. So let's take a break. Okay, please come back, a long break. Okay, please come back at 11:20. Okay, so we will talk about this. Okay.